So let's do this. Let's remember, or let me remind you of the results we got. So if I'm given a vector, thank you. Let me see if I can get this to be for me. There we go. Given a vector B and a vector space, could be a subspace, W, with basis set A1, A2, Oops, sorry. Okay. So I'm given a vector B and some vector space with a certain basis set. Nothing has to be true specifically about the basis set, it just has to be a basis set. So the fact that it is a basis set, what do you know about these A's? We'll say it goes up to AN just because. What's true about that set of A's? A1, A2, A3? They have to be independent. And of course they also have to span the space. I love it. So basis set is whittling down. So you could have a set of vectors that span a space. I could have 878 vectors that span R squared. I obviously have too many. So then I would pare it down to two linearly independent ones. I could take any two that are linearly independent. That would be a basis set. Okay, beautiful, beautiful. And we developed this process. So first off, we put these into a matrix A. And then here is the long and short of it. We found the projection vector using this incredibly obvious series of yeah. So what this does, and what's really, really, really neat is, I think I pointed out to you last time, if you pretend like the inverse is a reciprocal, which it isn't, it actually kind of boils down to the same form as the earlier, easier one we did. It's kind of neat. So there are situations where this does act like a division, but there is no true matrix division. So you just gotta be careful. I'm not gonna make you memorize this. I'm gonna give this to you. It's enough to ask you to be able to do all this. Yes? Does anyone remember what, well, can you guys, can anybody tell me what that is, that piece right there? Just, is it a rock? Is it an airplane? Is it a line?
Matrix.
It's a matrix. And what is that matrix? Yeah, it is this is the real power of this. Given this vector space, I could create the matrix that if I feed it any freaking vector, it will spit out the projection of the vector on the space. So that matrix P exists for a given W. And then I can feed it any vector, and then it will plop that down into that space. Yes? So I have this space here, and I have this vector here, and I can project that vector on that space. And then if somebody gives me a different vector, I could just use that same exact freaking matrix, because it just depends on the basis vectors. Yes? This was created from the basis vectors. This is created from it. This is created from it. Blah, blah, blah. This thing only exists given what I know about W. Okay. Could just be me that finds that neat. That's fine. So let's try a really easy example and then a freaky example. You should be able to answer this question without doing the work, but the nice thing about that kind of problem is we'll do the work and get the same answer. Yes? And then of course there are, for every situation you could do easily, there's 858 billion other ones that are not easy to do. So then we're like, thank God that the process exists. So here's the situation I'm talking about. I want to find the projection of 1, 2, 3 onto the space W, spanned by, not just spanned by, but spanned by, well, sure, 1, you can't even read your own writing, Jeff, good job. 0, 0, and 0, 0, 1. Are these independent?
Yes.
So this would make up a set of basis vectors. They span the space and they're independent, so they are a basis set. Can somebody, first off, can somebody reword this in simpler language as to what I'm asking for? Can anyone tell me anything about these two together? What do they constitute? The XZ plane. So another way to say this is I want to know the shadow of 1, 2, 3 on the XZ plane. Does that make sense? Maybe, maybe. And you can tell me the answer right now. No. It's got to be three-dimensional still. 1, 0, 3. So to smush a vector into a given plane, I just smush the one piece that's not represented in that plane. Because right now, how far is 1, 2, 3 away from the XZ plane? It's like 2 away. So if I just smush it down into the plane, that's its shadow. I should get 1, 0, 3 is the answer. Oh, so let's try this out. What do I need to figure out? What have I not put together yet? The very first thing. Got to put together A. So what's A? Nope. What is this?
Oh.
That's B.
Oh, it's 1, 0, 0, 0, 0, 1.
So what is the column space of A? What's the column space of A?
1, 0, 0.
You should be able to tell me in a single letter. What's the column space of A? W. Can you guys think about it? What are these vectors? They are the column vectors in this. Yes? So what do they make? I told you they make W. Yes? Is that okay? You stop for a minute. I know this class is trippy because you're always like, either the answer is insane or the answer is way too easy. And you guys kind of like try to go between the two of them, I think. I don't blame you. All right, I'm sorry. Does everybody see that? Okay. Does anyone not like answering questions when I say that? Okay. So, what else do I need to figure out? Yeah, what's A transpose?
1, 0, 0, reverse.
So you start to see a regimented way to do this. I need A first to get everything rolling. I need A transpose next. Because what's the next big thing I have to calculate? Yeah, the inverse. In order to get the inverse, I got to know what A transpose A is first. So, do you guys see this is a very nice example? Yes? Whole bunch of frickin' zeros and ones. That's beautiful. Can anyone tell me what's really, really, really nice about the columns in this? Can anyone tell me anything about the columns that makes them really nice? Besides, there's a bunch of zeros. Much more specific. What's the length of each one, each vector? Each column vector has a length of 1. Are the column vectors orthogonal to each other? Yes. Very easily, yes. Yes? Yes, yes, yes. Because you dot product them, boom, 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 and they're 0. Yes. You guys with me? And of course, we know this is x-axis, z-axis, so those are orthogonal to each other by definition. Okay, which is one reason why we built that the way we did. So, if you haven't already, while I was sitting there spewing stuff, did anybody calculate A transpose A? I guess not. Okay.
1, 0, 0, 1.
Yeah, it's awesome. 1001. That's too nice to believe, right? And again, I want to start with an easy example that we could do, you did without doing any work. Therefore, whatever the solution is, we already know what it's going to be. That's why this work is relatively easy in the middle. But I do this to help you buy into this process. If it didn't come out with 103, you could throw the whole thing, we can go home. And that's where everybody's like, I hope he makes a mistake somewhere. But I did this out ahead of time. Nah. Okay. So what's A transpose A inverse? You can't beat this one. Still 1, 0, 0, 1. You gotta love that shit. So, you got everything you need now to do this. Calculate do it. If only there were some O's, it could be potato. But O's in there. Look at that. We fixed it, guys. Good job. Thank you. Philip for the win. I thought for sure it was going to turn off right there. Okay. And there was a homework problem that kind of got you ready for something you could do here if you wanted to, where you can do this in clumps. There's that one problem that was like, this is X transpose A times Y, or I can't remember what else it was, like X transpose times AY, or it was like getting the same answer by clumping the thing you're doing in different ways. Okay, so it's A transpose A inverse, A transpose, and then finally B. So if you wanted to, you could do this product.
Wait, that one?
What do you mean?
So that's a 2. Oh, never mind. I read it wrong.
I'm with you. Good eye. You do have to be careful about the dimensions, but couldn't you do these two? And then couldn't you also do these two? And then you could do the result, yes? Instead of doing each one marching through. Now, obviously, this guy's sitting here. But I'm more talking generally. Okay. So go ahead and try to multiply that out, however you like. How did I do it? Let's see. I don't know what you did, Jeff. Oh, I see. Oh, I did do that. Look at me go. Right. So this times this can't be beaten. It's just this again. This times this. Huh? Careful. Here I get 1. Bless you. 3. Yes? You guys see that? It could only have 2 rows because that has 2 rows. So this is 2 by 3, this is 3 by 1, so the answer is going to be 2 by 1. Anytime you're multiplying by a bunch of matrices, you can just take a minute, look at the dimensions, make sure your answer is the right dimension. Sometimes you get cross-eyed and you invent rows and shit. I'm not speaking from experience at all. I've never done that. Okay. And then, of course, you end up with 103, exactly what we knew it was going to be. Okay, good. So therefore, the process can at least handle really, really simple situations. So let's give it a harder situation. Poor little process. Oh, by the way, before I forget, can somebody tell me what, this is really sucky with little p and big P. Can somebody tell me what big ass P is? I'm going to try to just, Which piece of this is big ass P? The first 3, yes? Because that's B. Okay. So then big ass P would be 100,001 times 100,001, which is that cool? Because I could just multiply by the identity, it stays the same, and then I gotta multiply by that. And if you do that, I believe you should get that. So what does that say? If I feed it any vector, that is going to kill the middle element. This is exactly what it's supposed to do. So it's not dependent on the vector I'm working with. It's just dependent on the space I'm trying to project into. That kicks ass. That's subroutine time. If you're going to work with the same subspace over and over and over again, you got a bunch of different vectors, you just have one subroutine to call up. If you're doing computer programming someday for some reason. Okay. Bless you. So let's still get a slightly, ooh, what else was it you wanted to do there, past Jeff? Oh yeah. What's the error? Does anyone remember how we defined the error? Yes. Do it again. So it's kind of, the reason I can't do P minus B is because B is a vector, P is a matrix, not the same dimension, I can't subtract them. But you do sort of want to do that? What do you got, Gene?
B minus x hat A.
Yeah, B minus, A x hat. And what was A x hat again? Does anyone remember?
It's just the projection vector.
Yes. And the whole idea we're trying to get to is what the hell with that. So if I want to know the error and I know the P now, here's what it's going to lead to. The error is going to be, this is if I'm in, I think this was if I was in 2 dimensions, talking about lines and such. So here's the extension for general situations. It's going to be this. Oops. It's supposed to be that way.
Is that big P or little P?
Yeah, I'm sorry, big P. And in that way, you've got the difference of 2 matrices, and then you can apply that to B. So that is, real quick, isn't that BI minus PB? Isn't this B? And what's PB? Little p. Okay, good Lord. So the error here is going to be I minus P. And here's P. So I minus P would just be 0, 0, 0, 0, negative 1, 0, 0, 0, 1. I'm sorry, 0. Jeff, I minus P. There you go. If I just take the identity matrix minus this, I'll end up with this. And if I apply that to my vector B, I don't know why I want that to be a 1 so bad. I'll just get 0, 2, 0, which is what we knew. We knew from the beginning it was a distance of 2 away from that space, which was just a nice plane. Okay. Okay. So the reason we kind of do it this way is so that if I do have a bunch of these, I could do this piece by itself, and then I'm just feeding it a bunch of those vectors. Okay. So you don't have to do it for each vector. Run out of paper. There we go. I got more paper. Use this too. Okay. So let's do this example. I want to find the projection of 1, 2, negative 1, negative 3 on W with basis vectors 1, 2, 0, 0, and 0, 1, 0, 1. Are those basis vectors relatively good? What's our current way to estimate that, to kind of see that? They both have some zeros, yes? What would be better is if they both were, how did we construct? Okay, good. So one thing I would take is if they both had a length of 1, and I could do that easily, yes? Just divide by the lengths they are. Even better than that, I wish that these were orthogonal to each other. Do we have to do any of that right now? No, I'm just getting us ready for section 4.4, which is one of the more important sections. We're slowly making our way there. All right, so get as far as you can with this. I'll wait. Did I finish this? Yes, I did. I even played around with some. I don't know what I was doing. Need any help, let me know. If you want to work with people near you, you can. Don't do it at all. You want to draw a little duck, you can do that. Okay, money, it's all you. Make sure everybody's starting off well. Here's your A, right? Just throw the vectors, the basis vectors in. And just remind me real quick, since A is composed of independent column vectors, what is a guarantee about A transpose A? It will be invertible. That's why the process requires me to invert it. I know I can invert it. It's not why it requires me, because I needed to do it to solve it, but it's kind of nifty. Just real quick, has anybody gotten A transpose A? What'd you get?
5, 2, 2, 1.
Yeah. I say that from memory. There it is. What did you get again? Sorry.
5, 2, 2, 1.
2, 1?
Mm-hmm.
2, I think it is. Yeah. Yeah. Let's see. I got this backwards, but oh well. 1. Let's see. Jeff, you could do it. That would be 5. Would be 2. Boop, bow. That would be 2, and that would be because it lines up with itself. Zach.
Yeah.
Okay. Gotcha. The ones line up, so you get 2. Okay. All right, keep going. By the way, if you're gotten the inverse, or you're about to, you're going to get a kind of a gross determinant. Not gross, but it's definitely worse than 1. You don't have to feed it in and multiply. You can take that outside and do it at the end. What is AD minus BC? So you get 1/6 out front. just leave it there. Do all the matrix shift, and then bring that in at the end. It's just a scalar multiple, yes? You don't have to work with all the fractions in the middle. You can leave the fractions till the end. Does that make sense? Okay. Now, if you're excited to work with fractions, then bring it in. Work with the fractions. It's all good. I don't want to take that away from you. Of course, to do an inverse of a 2 by 2 is nice. You switch these guys, and then make this one the opposite sign. One diagonal, they get switched. The other diagonal, they get negated. Not switched. So just don't bring the 6 in there. Did I get that right? Let's see. Trying to remember. Yep. Okay. Forgot what B was. There it is. Whew. Never forget, as weird as this collection of operations is, you all at least witnessed the derivation of it. We didn't make any of that shit up. We didn't go, let's put an A here. Let's transpose it. No, this just came out of the work. So it looks gross. It doesn't make immediate sense when you look at it. But I know it's grounded in derivation. Help. There we go. Ooh, stuff. Blah, 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 blah. Catch up with you guys. Has anybody done? I don't know if you guys like doing it the way that I suggested. It's up to you.
That's 2, 2, 0, negative 2 going down.
Oh, I see. Okay. 2, 2, 0, negative 2.
And then negative 2, 1, 0, 4.
Yes, that's what I got also. And if you do this clump,
It's 5, 5.
I got 5, negative 1, yeah. Let's see. 1, 2, 1, 2 is 5, and then 2 minus 3.
Oh, it's a negative.
Yeah, it's a negative 3, yeah. Sorry, buddy. There we go. It might have gotten sucked into the side of that. And then you got, but the 1, 6 can just wait. I don't need to make things more difficult for myself. So here you get, is this right? 12, 9, 0, negative 15? Is that what you guys got? And now you can't escape it. But the 6 works pretty well with some of these. Let's get 2, 3 halves, thank you 0, and then negative 5 halves. Is that cool? Now, real quick. Can you get a feel for whether or not this seems to make sense? No. No. This is a much, well, immediately, what dimensional space are we working in? R4, yes? So basically almost anything about R4 is difficult to visualize, yes? And these vectors are gross, they're not orthogonal to each other, and they're not unit vectors. The basis vectors for W were gross, they're relatively nice, but they're still way grosser than the first ones we had. So it's not like I can go, oh yeah, I expected that. No, I don't know. I have no idea. Okay. Maybe. The one little thing, well, no. Okay, I'm going to leave that alone. And then if I wanted to, I started playing around with this. What should be true about this vector? Can you tell me one thing that should be true about that vector? For sure. Okay, good. Okay, let's take that down to its next step. That is definitely in the column space of A. And the column space of A is W. So therefore that vector must be in W. You guys with me? Can you figure out your, how would you figure out the error? I could do this business again, yes? Which again, really is just B minus little p, which is, our B was, where'd it go? 1, 2, -1, -3. And our P is 2, 3 halves, 0, -5 halves. So if I do it either way, if I do it the matrix way, or if I just do it like this, our B vector and our P vector have to be vectors, not just because I just said the word vector, but because P is supposed to be a shadow of B. And then, subtract what to do. Okay, I almost don't care. Okay. So, that's that. So I can be talking about any dimension I want to be, and the process does not really fundamentally change at all. What's really nice about this one specifically is you might have been worried about this, but it turned out to be nice and small. Yay! Okay. So here's the next type of thing we want to work with. I might have asked you this already. Has any of you just happened to have taken statistics? You guys, okay. All right, do you guys, in fact, the rest of you might know this. Has anybody ever heard of linear correlation between two variables? Two variables being correlated mean that there is a snapshot apparent relationship between the two variables. That doesn't mean one variable causes the other one. In fact, this is a true statement. When teachers' salaries increase, liquor sales go up. Does that mean every teacher is a lush? Well, it definitely doesn't mean they're not, but it doesn't mean they are. What does it mean? So somebody could see that correlation and go, oh my God, who are these people teaching our kids? And I'm like, what's wrong with having a freaking drink? What's in there? My little What obviously happens is if teachers' salaries went up, more than likely, a lot of other people's salaries went up. In which case, the sale of almost every unnecessary item, and I don't know how you feel about alcohol, but it is unnecessary, then that would go up also, yes? So the whole idea of correlation is fraught with issues when it's real life data and we're trying to make predictions. You guys good? What we're gonna do is, it's got uses in data compression, for example. not optimization, but has anybody ever seen Silicon Valley? The show Silicon Valley. Like you have, you know what I'm talking. So they developed that. What do they call it?
I forget what it was.
It was something to make videos, for example, play quicker. It's supposed to compress. It was a compression algorithm. Yes.
Take less space on the hard drive.
All right. So where are my computer programmers? Anybody? So you guys, compression algorithm. Does that make any sense if I say that? So it's kind of like trying to figure out the least amount of data you must transmit, so the computer system that's getting that information can reconstruct what it was to begin with. So can you guys see that in your head? I've got an image, and it could be really high resolution, but I want to transmit that to another computer, and I don't want to take up a lot of bandwidth. So I'm going to try to see, is there a way to capture the most important aspects of this image? And then the computer will have software that will help it reconstruct what the original image was, so that in the middle, it's a low amount of data. Yes?
So it's like breaking it down into spaces.
Yes, so you can almost, I don't know if you guys are really with me or not, but I take this image, and it's multidimensional, and then I project the vectors that could represent anything about the picture into these simpler subspaces. Transmit that, and then I have the program on the other side that's going to kind of like undo what was done and put it back together. Obviously, those two programs have to be kind of like synced. It's not quite like encryption where you need a key for something, but you do have to know how was it compressed so I can uncompress it. Yes?
So when you're sending an image, why is it like sometimes it comes out of different resolution or not as uniform?
Because it wasn't a very good compression algorithm. Do you see what I mean?
Yeah.
Almost every compression algorithm, if you feed the same image over and over and over, eventually, it's sort of like taking a copy of a copy of a copy.
Yeah.
It will eventually start to show its flaws. It'll start to propagate errors. Does that make sense?
Yeah.
What was the thing that did that? I'm not going to remember. All right. Does everybody get the gist? Even if you've never, ever done anything with what I just said, does it make physical sense what I'm talking about? Okay. So that is one application of this. So the next thing we're going to talk about is this idea of how do I best fit given data. So in statistics, we actually call it a best fit line, for example. And that's what I want to start with. And I'm not going to suddenly teach you statistics, but I do want to set this up. Let's say I want to find the line that is closest to.
This is 4-3.
Yeah, this is 4-3, yes, thank you. Find the line that is closest to the points 1, 3. So far, so good. 2, 6. All right, this is really good. Yes. Good job, Jeff. 3, 6. Damn, Jeff. Damn it. Jeff. So, of course, everything with the shit at the end there, yes? There is not a line that connects all of that data. I want to get the line that visually averages those data points. I want the line where the squares of the distances from every point of that line is minimized. So that's why we call it a least squares line, or a least squares approximation to be more general. Because obviously we're not going to always be talking about lines. Let me stop for a minute. You guys semi with me? Can you guys just real quick graph that? Just semi-decently make a little sketch by hand. Graph those points. So try to put a little bit of effort. Don't just go. So I got 1, 2, 3, 4, 5, 6. 1, 2, 3. Doesn't matter. These don't matter. So 1, 3, 2, 6, 3, 6. Okay. Now, can everybody that has done that, can you go and try to draw in a line that you feel graphically averages those 3 points? Now, normally you might use a pencil because your first attempt, you could tell it's wrong. For example, we're not going to be doing a ton of this, so I don't want to spend too much time on this, but if I draw this, how do I know that's wrong?
There's no other points on it.
There's more points below, so the average distance is not minimized. Yes, I should have a balance. Did I pick a good pencil? Maybe. Or not really. Shite. Does every eraser suck nowadays? Okay. So a decent, now let me see if you guys, I'm gonna do this because I'm weird. Well, I already know the answer, so I shouldn't do that. Let's see. So if I had to guess, I would say maybe something like this. That kind of makes that a little big, but then these are pretty tiny, and I have two on one side, but the other one is kind of balancing those two. I don't know if you guys see what I'm talking about. There's two on one side, but the one on the other side is relatively further away, so everything kind of balances. Now, if I really wanted you to, you could find a slope in the y-intercept of that line, yes? Or whatever line you drew. So for me, it looks like my y-intercept would be maybe just a bit over 2, yes? So I'm going to say my y-intercept looks to be 0, 2.1. And if I had to guess my, or maybe it's 2. I don't know. Who knows? I'm going to say that. And then let's say 2. And if I had to do my slope, it goes up 1 over 1, it looks like. So my slope looks to be 1. So you could all do that for your picture, correct? You can give an estimate at least for those things. Now, in reality, I'm probably going to have a lot more data. I'm not going to want to do that shit because I'm probably wrong. Right? Look at my scale. Just look at it and go, good God, you teach this shit? Okay. Sorry. So again, we're starting with a very, very simple example where we can kind of see what makes sense for what the answer should be, and then we're going to actually get the answer. Now, what was the whole purpose of the stuff in 4.2? What was it trying to do? What am I actually trying to do to E, the error vector? To get a good projection, I want the error vector to be small, the smallest I can make it. Isn't that pretty much exactly what this wants me to? So these little things here, these little vectors, these are like little e's, little errors. I want them, and the square of them, because some could be negative or whatever, the square of their lengths to be the smallest they could be. Let me say this all again. The sum of the squares of the lengths to be the smallest they could be. So what's really kind of funny is I could use all the same method we just did. So let's build up to where I can see the elements of what I need for a problem like we had in 4.2. Right now I just have these disparate points staring at me. Let me ask you this. I use slightly different letters in the book. What did I end up with? Oh yeah, here we go. I ended up with MT plus C. I don't want to use X because X has some meaning for us. It's normally a vector that I'm trying to solve for. I don't want to use B for damn sure. Right? MX plus B, so I made it MT plus C. You guys with me? The book uses C and D. I don't know why. I'm going to use M because that's obviously the slope. Yes? Okay. Can somebody help me? What values of T are we talking about? No. What are the values of T? Here's my points. 1, 2, 3. So for T equal 1, I get, and I'm trying to figure out what this is going to be. For T equal 1, I want C plus M to be what? In fact, I'm sorry, where did I get this from? If T is 1, isn't the C plus M times 1? Okay. So what do I want that to be? 3. Is everybody with me? For an input of 1, I want the output to be 3. For an input of 2, that would be C plus 2M. I want the output to be 6. And for an input of 3, C plus 3M, I want the output to be 6. Doesn't it already? Can't you make a matrix out of that? Yes? Now be careful, don't augment it. Just make the matrix, this is basically AX equals B, but it's truly, what, Jeff? It's kind of like A CM equals this thing. And that we'll call B. Yes, okay, because that's what it should be. Can you write what A is? Again, just a system of equations. That's the first level of throwing things into matrices. That's the most basic shit matrices do, is they solve those for us. And the matrices are like, we do a lot more shit. And you guys are like, yeah, we know. You do too many things, damn it. What is A? One? 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 1, 2, 3. Are those literally independent? How can you tell so quick? Yeah, there's only 2, so they're not multiples of each other. Yeah. It's only when it gets to be more than 2 that sucks. Everybody, I think, is past the point where you just take pairs and go, well, there's a multiple. No. If I have 3, one could be a combination of the other 2, and it could be a combination you don't even think about. So if I did have 3 vectors in there, what would I do? Row reduce, kick ass. And then I'm hoping to not see a row of zeros. Okay. And by the way, how would I get in a comparable thing this matrix to have 3 vectors? Wouldn't you agree that a parabola would fit this better? Wouldn't you agree? Because that would allow it to have this arch that it kind of has, yes? So then that would be mt squared plus dm plus c or whatever the shit, yes? And that would have 1, 2, 3. That would be a, yeah, okay. You guys are with me. That would be quadratic correlation, or quadratic regression, blah, blah, blah. Okay. So now, if I just do the same thing, so here's the idea, before I go too far with this. We've got all the elements we need. What's B, by the way? 3, 6, 6, 11. Kick ass. So we can start attacking this thing, but I do want to say a couple things in general. Before we kind of attack this. This is the least squares solution to AX equals B if E is smaller, is the smallest possible when we project X onto the column space of A. So do you all agree that, let me see how do I want to say this. Well, let's see. All right. Can you guys do this for me? Well, real quick. How do I say this? Can you augment that? How do I do this real quick? Who's got your calculator with you? I'm really curious about this because I don't have my TI calculator with me. Can you put 1, 1, 1, 1, 2, 3, 3, 6, 6 all together on one matrix? If this is in the column space of these, what should I get when I augment, when I put this in? How do I say that in a different way? Let's see, what do you get?
You remember this?
Yep.
The identity.
The identity, okay. So if you put B in with A and row reduce it, you get the identity. Now, in general, let me see, how do I say this? what would that mean is true then about these 3 column vectors? Yes. So is this in the column space of these? No. This is going to become big in like the next section especially, but when I cannot solve AX equals B, this is one specific procedure to kind of address that. In the next section, we're actually going to kind of generalize that procedure a bit. B is not in the column space of A. In fact, we knew that from the beginning. That's why we had an issue with it. We can't get the line because there is no line that goes through all 3 of those things. So this method is going to project B into the column space of A, and I want the error to be as small as possible. And that is exactly what the process in section 4.2 did. Is it in doing the projection process, I am minimizing the error. That is how we built it. It does exactly what this thing needs us to do. Okay. Jeff, you speak a lot. I know. You got so much shit to do. I know. Okay, all right, let's just do this kind of together. Gee, Lord, especially considering I have run out of paper. Do I have no paper? Damn it. I always forget to bring more paper. Sure, he's getting some brownie points. He's got lines. I'll be all right. When I was a student, I always hated using line paper. Okay. All right. I guess somebody's got to keep me straight. All right. So we have our A. We have our B. Now I just need A transpose. Let me rewrite what A is. 1, 1, 1, 1, 2, 3. A transpose. I'm going to kind of do this a little bit because you've already gone through this method once, but I want to get to the answer so we can see, and I want to show you, well, we'll see. We'll get there. We'll get there. Where'd it go? Here we go. A transpose A. I, past Jeff, got this. I feel pretty good about this because everything seemed to work out in the end. So you can see that if you want to. 3, 6, 6, 14. A lot of 6s today because I'm evil. Oh, this is where that happens. I'm being silly. Ah, here it is. Perfect, perfect. Okay, is everybody with me so far? Okay, now. Let me back up a step. Damn it. So much. All right, hold on. Don't nobody give me anything. Hold on. Oh, you brought nothing. Okay, I'll make this work. Sorry, I thought this next step was coming later, but it's right now. When AX equals B has no solution, one thing we can do is we can multiply both sides by A transpose A. If I do that, I end up with A transpose, no, I'm sorry. I got ahead of myself. A transpose. Multiply those sides by A transpose. If I do that, I get A transpose AX equals A transpose B. Now, I do not blame you at all if you have forgotten that that was one step in the long-ass process we went through to develop the method of projecting vectors. And I don't know if I can find that quickly for you. Probably not. Damn it. Because then we subtracted and we figured out what inverse was and we went for there. Okay. So if I am here, so let's see. If this does not have a solution, I do this. What does that do? What kind of matrix will this always be at least?
Invertible. Well, actually, no. Symmetric.
It'll be at least symmetric. It'll be at least square is the good thing to say. You guys with me? It'll definitely be square. Okay. if A had linearly independent column vectors. Now hit me with what you just said. A transpose A would have to be invertible, which means as long as A itself has linearly independent column vectors, and since that did not have a solution, okay, there's a lot coming at you. If A had linearly independent column vectors and AX equals B has no solution, what had to be true about A by itself? Could it be square? If I have a square matrix composed of linearly independent vectors, it has to be what? If I have a square matrix where every vector is linearly independent, which means I can do what to it? Inverted, which means AX equals B would have had a solution, yes? So the major thing that if A has linearly independent column vectors, it should be like, it's like a really good, relatively good matrix, yes? It's better than a lot of other matrices we've seen, right? These little rough-shod matrices. Get it? So if I multiply it by A transpose, I'm making it square. Therefore, that has an inverse. And then I can solve that associated equation. I wish I could find, just to kind of show you, dadgummit, I don't know if I brought that piece of paper with me, but this is where we, don't get that all mixed up, Jeff. This was one step on the way to developing the process. And I'm not gonna find that, am I? Oh, poor little Jeff. Too bad, okay, too bad for everybody. So, coming back to our problem. Here's A transpose. And here is our original problem. Let's see, where'd my A go? Here it is, okay. 1, 1, 1, 1, 2, 3. CM. This is 3, 6, 6, right? Yes. So if I attack both sides of this with A transpose, you guys, we've already figured this out, yes? We figured this is 3, 6, 6, 14. We did that up here, yes? Okay. And what is this? Can you guys take a minute and figure out what that is? You know what A transpose is? You know what B is? I wish you could. Ah, it's okay, Jeff. You left it somewhere. Yes, 1533. Okay. Oops, I left out my X. That's really bad. And now, of course, how do I solve that? How do I solve it? Figure out A transpose A inverse and multiply the other side by it. Because now we're sort of borrowing a part of our process for finding projection. I'm not as interested in the projection as I am. So this vector would solve this equation. When we solve this, we're actually getting our x hat. We're not going to get the vector that would solve this equation. Why can't I get the vector that would solve this equation? Because no combination of these gives me this. You helped us figure that out. So over here, I'm not going to get the actual answer because there is no answer. I'm going to get the next best thing. I'm going to get the closest thing to what the answer could be. So in the case, to make it realistic, I've got these 3 points. There is no line that goes through all 3 points, but there is something that gets closest to going through all 3 points. That's what I mean when I say get the next best thing. So if I do this, What do I freaking get? So first off, I got to figure out the inverse of this, yes? No idea if somebody already did that, knowing kind of like where we're headed a little bit. But I got, let's see, past Jeff, what'd you do, buddy? I got 1/6 again, 14, -6, -6, 3. So I'm going to multiply this side by that. Good Lord, Jeff.
Wait, what about the 1/6?
Say again? Oh, sorry, 1/6. Thank you. And if you do all that, and again, the 1/6 can just wait till the end. You should get this at the end. Somebody remind me what was m, of course. I specifically named it that because that's the slope. So the line 3/2 x plus 2 is the line that will get the closest to all three data points. So I could have done that same thing. I would have made a larger A matrix, but I could have tried to get the best fitting quadratic, best fitting parabola. Yes? I almost said parabola, which is funny. Okay. So if you've taken EV stats and you did that before, this is one way to show a process to get that. Where we're headed, by the way, finally, is we're going to figure out, I keep talking about this, the next section is kind of like we're going to, if I'm given a basis set of vectors for a space, I want to make that the best basis set. What makes it the best? Two things. They all have length 1, and they're all orthogonal to each other. Now, they're automatically independent. So if somebody gives me a basis set and they're all gross, I want to make a process, I can feed it to it, and it spits out orthogonal unit vectors. We're going to develop that somehow. And all the time that
You have a stapler by any chance?
Stapler?
Yeah. Also, what do the annotations on top of the homework mean when it says like okay or correct?
Okay,